So before I start, let me say it's more than a pleasure for me giving a talk here at Princeton, and I should say thanks for Professor Yao, unfortunately is not here, for invitation, and Professor Fyodor for arranging this. And I know this is maybe the audience knows very well about random matrices, so I'm not a probabilist, I'm a topologist, and I'll try to give what was like recent developments on random algebraic topology using random matrix theory, but I might say something in random matrices which is totally obvious to the audience, so I should say I'm sorry. But maybe it wasn't that obvious for me at the beginning. Okay, I should start maybe. So the title of the talk, it's gap probabilities and applications to geometry and random topology. So I want to start with the geometry aspect. So I'm going to ask a question in geometry. So let me say question 1. I consider the space sigma n. So it's going to be the set of matrices, symmetric matrices, n by n with real entries, with determinant 0 and Frobenius norm 1. So essentially, this is the set of singular symmetric matrices, n by n. And the first question is, what is the volume? What is the volume of sigma n? So what I'm actually asking here is, so we have a vector space, which is the space of symmetric matrices n by n. So let me call this a vector space of dimension n times n plus 1 over 2. I'm going to call this number capital N. And then we have a scalar product in this vector space, so which is actually the most natural, the Frobenius norm. So this is going to be just a trace of q squared. So I have a unit sphere inside this, right? So sphere S n minus 1. And this sphere is endowed with a Riemannian metric, just a standard Riemannian metric coming from the scalar product. And then there is this algebraic subset here. So let me just give you a picture. Let me tell, for example, n equals 2. Then the space of 2 by 2 symmetric real matrices is just isomorphic to R3. So this is going to be the cone of matrices with determinant 0. So this is sim 2R. This is going to be the unit sphere inside this cone. What I call there, in this case, it's just an S2. And then I take the set of singular matrices. So this is determinant 0. Determinant equals 0. Okay, so the question is, all right, we have in this case, it's just a smooth subset of the sphere. It's like the union of two ellipse shaped. Actually, they're really ellipses. And then the question is, what is the volume of this subset? So in this case, the answer is simple. The volume of sigma 2. I'm going to denote with volume just to avoid cumbersome notation, just this, like if it is a modulus. It's going to be actually volume. It is 2 square root of 2 times pi. Right, the answer is was extremely simple, but what I'm asking is in general, what is the volume of this set? So the computation of this volume might be interesting from the geometric viewpoint, but it's also interesting for numerical analysis, because essentially the order of growth of this volume as a function of n, it tells you somehow like the probability that a linear system involving symmetric matrices is ill-conditioned. But my motivation is mainly so for the moment, just the geometry of this object. So by the way, it's good to notice that this is singular. So it's an algebraic variety, and it has singularities. So like in general, you don't see it in this case. But if I say, for example, I take a 4 by 4 symmetric matrices, there are singular points inside. What I'm actually asking is the volume of the set of smooth points, right? Okay. So just let me mention, might be interesting to ask the same question maybe over C. Maybe I want to put this here. So over the complex numbers, I can ask exactly the same question. So I can ask for the volume of symmetric matrices with complex entries. And then, I mean, somehow the answer is it's a trivial and it's extremely simple, and it's related just to integral geometry formula, and it's just sorry? No, real symmetric, really symmetric.
Complex symmetric.
Yes, complex symmetric. Yeah, I'm just saying, just complexify this problem. So take the entries and let them to be complex matrices, complex numbers, right? So there's not going to be just A transpose equals A, but the entries are complex complex numbers. But it's good that you ask, because in fact what I want to study here also later is I could say that this results I'm going to present generalizes to Hermitian matrices as well, and then the complex counterpart is going to be this. So Hermitian should be thought not as the complex counterpart, but somehow like as the GUE counterpart. But yeah, so in this case the answer is just n times the volume of the sphere of dimension 2n minus 2. And essentially this equality here, it's extremely easy to derive, and it follows from this so-called integral geometry formula. So it comes from averaging the function that intersect a plane in the space of symmetric matrices with this. So we take a plane in the space of symmetric matrices, complex. We intersect with this object, and we average the number of intersection points over the unitary group. And integral geometry formula tells that this gives the volume, but on the other hand, this gives exactly a degree of this, which is n. I'm not going to go into details. I just want to mention that this is a classical, and it's just integral geometry formula. In fact, to be honest, just give me your favorite complex projective manifold of degree d, and then you ask what is the volume of this complex projective manifold. The volume is exactly d times the volume of the complex projective space of the dimension of this manifold, which is pretty much what I'm saying here. All right, so now I want to say that, unfortunately, comparing with the complex part, it doesn't really help. So we have a lot of theorems in mathematics that they compare the size of some object defined over the real numbers and the size of object defined over complex number. Let me just with a simple example. So I will call this R versus C. So simple example, just let's take the number of real roots of a polynomial, right? This is definitely smaller than the number of complex roots. Let me put maybe a C here and a R here. But this is typically the degree if the polynomial is generic. Just polynomial in one variable, that's kind of trivial. Let me say this is actually interesting and related again to the integral geometry formula. Let me pick a real algebraic manifold in the projective space, and let me compute its volume. Let me call the manifold is this. This is the volume, and let me normalize by the volume of the real projective space of the same dimension. Well, this is bounded, again, by the volume of the complexification divided by the volume of the complex projective space of the same dimension. So we might get the volume for this manifold. We might get an upper bound using this formula here. And you see these two properties, they actually compare geometry over R and over C. So this is geometry. What I find it's like the most surprising is that you can also compare the topology. So, and this is called the Smith inequality. And I'm going to tell what does it mean. So Smith inequality says, this is for topology. Smith inequality says, all right, give me a real algebraic variety, and now count the sum of all of its holes. You typically, topologists call this sum the total Betti number. So take the sum of all possible holes of every dimension of the real part. Well, no matter how this all distribute in the different dimension, the sum of all of them is definitely smaller than the sum of the number of holes over the complexification. Take this example. If the complex algebraic variety is just the zero set of one univariate polynomial, the number of connected components of the zero locus of a polynomial is less or equal than the number of connected components of the complex part, just the complex degree. If there is any of you who is familiar with algebraic geometry, this immediately provides the so famous Harnack bound for the topology of real algebraic curve in the plane. So essentially, a real algebraic curve of degree d in the plane has at most d minus 1 times d minus 2 divided 2 plus 1 ovals. And its complex part as genus 2g plus 2, which is d minus 1 times d minus 2. So d minus 1 times d minus 2 plus 2. So this is, again, the same inequality. It's a very general inequality, and I'm going to talk about that later. So for the moment, I just want to say that there is a way to compare geometry over the real number and geometry over the complex numbers, but there is also a way to compare topology over the real numbers and topology over the complex numbers. OK, let me tell you what is the answer in general to this question. What is the volume of this sigma n? And then let me tell you how to derive this answer using random matrix theory. So the answer is the following. So answer. This is. I forgot to mention something. Maybe it's because I was excited of giving a talk at Princeton. I'm going to present joint work with Eric Lundberg, who is here with me. So we are both postdocs at Purdue University. And this theorem is joint work with him, so it's a recent theorem. All right, so the volume of set of singular matrices for Frobenius norm 1. It is, we have an exact formula, but for the moment I'm just going to write down the asymptotic. So let me normalize by the volume of the sphere of the corresponding dimension. This is just computable, right? It's just we use this gamma functions and pi to some power. Well, this is asymptotically when n goes to plus infinity. It gets equivalent to 2 over square root of pi n to the 1/2. In fact, we have an explicit formula for this volume here. I'm just writing down the asymptotic in order for you to see that how does it look like. Let me just notice that the order here is the square root of what was happening over the complex numbers. Over the complex number, if we normalize by the volume of the sphere of the corresponding dimension, we get n. And over the real numbers, we get square root of n up to a constant. All right, now I want to tell you why should how could we prove this this computation using random matrix theory? And in order to prove that, I want to rewrite this asymptotic here. Actually, this as minus square root of pi over 2 times this function. And this is going to be the derivative of the gap probability at 0 in the GOE ensemble. Okay? So for now, it's mysterious, but I'm going to reveal what is the mystery here. So let me say just some probability. So I want to consider, well, everyone here I think knows what is the GOE ensemble. So it's an ensemble of essentially, what is going to be useful for me is that it's this space with a probability distribution which is uniform on this unit sphere. That is the part that is going to be useful for me. But typically, we can have different distributions, so the different definitions. So Q is so the probability, let me just recall this, that a matrix Q in the space of symmetric matrices belong to some domain D. It's just given, well, there is a normalization coefficient to n minus n alpha, and then pi to the minus n times n minus 1 plus 1 over 4. And then there is the integral over this domain, e to the minus norm of Q Frobenius square. And these are the matrix elements. OK, this is classical. And what actually I need is the joint density for the eigenvalues, which is the main ingredient for the computation of this volume. So the probability that lambda 1, lambda n, they belongs to some region B. It's just given, well, there's a constant, a normalization constant. And then it's the integral over this region B, e to the minus sum of lambda I squared divided by 2, and then product norm of lambda I minus lambda j, so d lambda 1 t lambda n, and here is I is smaller than j. Okay, this is just a joint density for the eigenvalues. Okay, this is what I need in order to give you a proof of this statement. And we proceed as follows. All right, so we have to evaluate the volume. So we have a sphere, right? And then there is a subset of the sphere. I'm just making this picture, which is small dimensional, but just to understand. All right, so this subset, you see, it's where the determinant vanishes. So it's actually codimension 1. So as dimension 1 less than dimension of the sphere. So the volume of this, I hope you see, yeah, the volume of this, it's actually given in this way. So we take a tube of radius epsilon around it. We divide by 2 epsilon, and we send epsilon to 0. Why is that true? I mean, just imagine we have a subset of the sphere of codimension 1. So this could now the black work is the sphere. I take a tube of radius epsilon. This tube really means in the Riemannian geometry, the set of all points whose distance is less than epsilon from this. And then I take the volume of this tube. And then the volume of this tube, it's going to be asymptotically 2 epsilon times the volume of this. So the derivative of the volume of the tube at 0 divided 2, it's going to be the volume of my hypersurface. OK, this is the first step. The second step is identifying this tube. And here is where I want to use the eigenvalues of the matrix, because essentially there is this theorem. It's called Eckert-Young theorem. Eckert-Young. It says that if you pick a matrix X and you want to evaluate the distance between this matrix and the set of matrices with determinant 0, that's exactly the least singular value of X. Least singular value of X. It's an interesting theorem in the geometry of the space of matrices. And it can be generalized to the space of symmetric matrices. So we can take the distance here in the space of symmetric matrices, and to be determinant equals 0 actually our set. And we get this slightly generalization of Eckert-Young theorem. In fact, the proof is exactly the same. So what Eckert-Young theorem says is that the set of matrices that are in an epsilon neighborhood of determinant equals 0 are those matrices for which the least singular value is smaller than epsilon, right? So this allows me to identify this object. So this is going to be the limit as epsilon goes to 0 of 1/2. And now identifying this object is a set of all matrices, so Q belonging to the sphere, such that the least singular value is smaller than epsilon. I denoted sigma Q the least singular value to epsilon. This is Eckert-Young theorem. OK, so now let's see. Let me make again this picture here to understand what's going on. So we have this sphere, right? And then we have a subset of the sphere. Say, now I'm going to depict this way just because I need a two-dimensional picture. So this is this subset. There's a epsilon neighborhood. This is this least singular value less or equal than epsilon. OK, now let's see. Inside the sphere, so if in general, now let me take the like a cone generated by this set. And now here is where random matrix theory enters. Because you see, since the probability distribution in the GOE ensemble is uniform on the unit sphere, if I consider this cone here, the probability of this cone in the GOE ensemble is the same as the volume of the intersection of this cone with the sphere, right, divided by the volume of the sphere. In general, right, if I have a set which is homogeneous by dilation, which is the case of the GOE ensemble, so I have a subset here. So I know that the probability distribution, it's uniform in the sphere, and I have to evaluate the probability of a cone. So it's the same as the amount, so the fraction of area covered by this cone over the sphere. So that means that you see, what I have here, it's the volume. But I can relate this volume to a probability. So the next step is just writing down this as the limit as epsilon goes to 0 of 1 over 2 epsilon. And then it's going to be volume of the sphere times the probability that the least singular value is less or equal than epsilon norm of q. Why there is this epsilon norm of q? Just because I'm extending this to a cone, so I have to take an homogeneous extension. All right, you see, now we're done, because this here, it's just 1 minus the probability that the least singular value is bigger than epsilon norm of q. Okay. And now this is almost the gap probability. So the gap probability is that the least singular value is bigger than just epsilon. Here there is a norm of q, right? So essentially the gap probability evaluates the probability, say, of a cylinder in a sense, but we have to evaluate the probability of a cone. But then in the limit, these two probabilities, they are related by a gamma function factor. So I don't have enough place here, so I'll put it here. So the next step here is just relating in the limit the probability of a cone, which is what I need, with the probability of like a cylinder, which is the gap probability. So in the limit, this is just going to be there is a constant factor which comes from comparing the cone and the cylinder, which is square root of 2, and then there is a gamma of n half divided gamma of n minus 1 divided by 2. And then there was a constant coming from the volume of the sphere. And then this is a 1 minus, so we have a minus the derivative of the gap probability. And then we have a 2, and then we have the derivative of the gap probability at 0. So this is now going to be Fn epsilon is gap probability at epsilon in the Jury ensemble. So that's an exact formula. So the exact formula tells you that this, oh, by the way, this constant over here, it looks ugly. It is actually the volume of the sphere of dimension n minus 2. So this computation,
what happened to the
yeah, there is a square root of 2 over pi. Yeah, square root of pi over 2 as well. I agree. Yeah, there is also this constant. All right, so now you see, at least I gave you a proof of this formula, which is exact. But then,
because your right-hand side doesn't have an n at all. I mean, except there. But
this one?
An n in the constant.
Yeah,
in fact, have an n in the constant.
Yeah.
In your calculation, you happen to have these two independent
sure.
factors.
No, I agree. But you see,
there must be a
no,
geometric reason that's
no,
true.
yeah, no. But so you see, there is this volume here. So in the left-hand side, I'm dividing by this volume. So I'm bringing this volume, this.
I understand that, but I'm saying there's a you've written the constant 1 or the constant square root of pi over 2
Yeah.
as a product of two n-dimensional factors. The product of the volume of the cone to the cylinder and the product of the spheres. They happen to cancel. There must be a geometric reason they're canceled.
So like a say physical reason or like a dimension.
Geometric. They're both geometric factors. One is a ratio of volume.
So I think that no. But you see, I think they don't really cancel because there is a volume of the sphere here as well. Another sphere. There is a volume of another sphere.
No. But after you're taking the ratio of two volumes of spheres, multiplying it by a ratio of a volume of a cone and a volume of a cylinder.
Yeah.
Those happen to cancel. There must be a simple geometric.
No, but this is not a number.
No. But again, if you look at just the numerical factors.
Oh, you're saying why this part here
Those numerical factors
turns out to be.
Are a product of two ratios. Of
No, I understand what you're saying.
And they happen to be almost the same.
Yeah.
There must be some reason.
I don't know. Okay. I don't know. No, but actually I know what you're saying. So you're talking about like going from this just to this step.
Correct. And
Okay. Well, maybe I think maybe I can tell you a little what I think it's my intuition about the reason. The intuition about the reason is that when you compare these two volumes here, you actually, to compare there in the limit, you pass to integration in spherical coordinates. I think that's the reason, yeah. Because you integrate in spherical coordinates, and then there's going to be a gamma function because there is some exponential, but then this is the
But it's the same gamma function that enters in the ratio.
Yeah, yeah, that is true. It's the same, yes.
Again, the gamma functions have dropped out.
I think
there
it's...
There are gamma functions in the sphere. There are gamma functions in this calculation. Gamma functions in this.
Yeah,
I
I think that the reason is really that when you go to polar coordinates, that's exactly what matters. But if there is a more deep reason, I don't know. Okay, so maybe I should tell just maybe say one remark here. Oh, by the way, the evaluation now of this limit here. So to prove that this part here so essentially the evaluation is that the asymptotic analysis of this, it's going to be a minus 2 over, so 2 square root of 2 over pi n to the minus 1/2. So this is delicate actually. So what is classically studied is first we let a rescaled limit n go into infinity, and then we take epsilon go to 0. But here we really need n fixed, and then epsilon go to 0. So it's kind of delicate, but actually can be done because in a sense we have all the ingredients, because it's just now what we have to do actually. This b is going to be minus infinity epsilon minus epsilon union epsilon plus infinity to the power n, and then we have to take derivatives. So it's a kind of fundamental theorem of calculus, but then evaluating at 0, all the things they match together, and they give this asymptotic analysis, which is part of the result, I think, unless it's already known, and I wouldn't be surprised actually if it is. And then there is another remark I should say that about this Hermitian and complex, which is I can definitely replace here with the so-called, so instead of working with GOE, I can take Hermitian matrices or quaternionic Hermitian matrices, and in fact I can take a more general, I can take more general this Dyson gas model, and so I can take a beta positive, and I can evaluate, say, I can ask for what is the derivative at 0 of the gap probability, right? And then this, this is an exact result, minus 2n times c beta n divided c beta n minus 1. And these are the normalization constant for this beta ensemble times the expectation of the modulus of the determinant to the power beta, but over an ensemble of dimension 1 less. So this asymptotically is this. So these computations work for every beta bigger than 0, and it's just using again the joint density of the eigenvalues. So it's just simple, not simple, but just analysis. All right, now, so I want to jump to another problem. I'm going to use this result, and I'm going to ask the second question. So this is going to be now, so random algebraic topology. So, all right, I want to ask this question. So question 2. What is the average topology? And I have to explain what does it mean. Average topology of a random intersection of k quadrics in RPN. I have to explain, I think, actually, almost every single word in this question. And I want to start with just to give an example of what is the motivation. Again, let me consider 2 conics, so k equals 2, so 2 conics in RP2. So I have 2 quadratic forms. So I have Q1 and Q2. These are homogeneous polynomials of degree 2 in 3 variables. Of degree 2 in 3 variables. So I can associate to them symmetric matrices by mean of a scalar product. And these are symmetric 3 by 3 real matrices. So why am I taking homogeneous polynomials in 3 variables? Just because usually when you want to define a subset of the projective sphere, a projective space of dimension k, you need something homogeneous in one more variables than k. In fact, you can think about just taking the zero locus of these two polynomials on the sphere in R3, and then take the double cover to the real projective plane. But if you don't feel comfortable, we can just set one variable to be equal to 1, and that's the same description. All right, so what can it be? So in general, we can have like the two conics. This is now the projective plane that do not intersect, or they can intersect at 2 points, or they can intersect at 4 points, right? At 4 points. So we have, say, 2 points, 0 points of intersection, 2 points of intersection, 4 points of intersection. Now, what if I pick, now I ask you, what is the average behavior? So now what if I pick these two quadrics random? And by random, I really mean that the two corresponding matrices are in the Gaussian orthogonal ensemble. So this probability distribution, it's classically called the cost line distribution. And it's the unique probability distribution on the space of homogeneous polynomial of degree 2, which is invariant by unitary change of coordinates. And it corresponds to say that if I to every quadratic form, I can associate asymmetric matrices by this identity. It corresponds to the corresponding symmetric matrices being the GOE ensemble. So random here means that Q is GOE. I need one more variables because we are in RPN. OK, so now let me ask the question, what happens on average? You see, I have an a priori bound, which is 4, because we cannot have more than 4. And in fact, it again comes, if you want, from this inequality. But what is the average behavior? So we definitely know that the average number of intersection, so every average number of, let me call the intersection of these two conics x. The average number of points in intersection, we definitely know is less than 4. There can be more than 4. But actually, it is exactly 2. And this is a classical result due to Schub and Zmail. So what I'm asking here is, oh, I have one more blackboard, so but I'm going to use this one. What I'm asking here is more generally, now if I take, let's even stay with a case of two conics, but not in the real projective plane, maybe in RP3. So now I have two hypersurfaces that intersect in RP3. They intersect along a curve, along curves. So this is no longer points, the number of the intersection, at least for the generic choice of these two conics. And more generally, if I intersect, say, k of them in RPn minus k, I'm going to have a random subset which has dimension n minus k. So each one like defines an hypersurface, and then the next one defines an hypersurface in this hypersurface. So each time the dimension drops down by 1. And eventually, we have this set x here, which is going to be where q1 equals q2 equals qk equals 0 in RPN. And the dimension of x is going to be n minus k, right? So if k equals n, it's just going to be 0, means points. So now what I want to ask is, what is the average topology of this set? Average topology actually means it's Betti numbers. What does it mean again? Well, so Betti numbers, BI. So the ith Betti number counts the number of holes of dimension I. So for example, B0 is the number of connected components. B1 is the number of independent loops in this set. So it's the number of independent loops. And then B2 is somehow the number of independent like cycles of dimension 2, and so on. And what I'm going to ask is, what is the average behavior of these numbers? So you see, it's a much more complicated problem than just counting these points. And the reason is that this result of Schuben's-Mail essentially uses, again, the integral geometry formula techniques. So it should be interpreted as a computation not of the number of connected components, but really of the zero-dimensional volume. The volume of this, on average, it's known, and it's very easy to compute it. And it's the square root, it's the expectation of the volume of this. It's just going to be square root of d to the power k, sorry, 2 to the power k, times the volume of rp n minus k. And if you just take now n equals k, you get this case. This is a Schuben's-Mail result. OK, before I proceed, and then so in a sense now, I want to take a step back to this list of inequalities I presented here. So you see, here we were comparing something happening over the real and something happening over the complex. So it's a classical result that if I take expectation here, maybe I'm going to make a new table, which is better. So let me ask the same question now. Instead of counting the number of real roots of a polynomial, let me count the average number of real roots for a polynomial which is cost-long distributed. So a distribution of probability is invariant by the unitary action. So if I take expectation of the first one, number of real roots, classical result, we get square root of d. So which is, by the way, the square root of what we get on the left-hand side, number of complex roots. This is if the polynomial is cost-long distributed. So cost-long, you can think it means just a distribution which is invariant by a unitary change of coordinates. If I take expectation in the second one, this is a Schuben's-Mail result. Expectation of the second one. I get a square root of the right-hand side. And this is what about the geometry, right? So geometry. Now question is, what happens if I take expectation of this one? Okay. So first of all, I don't even know for the moment what's happening on the right-hand side. So maybe I should give you a picture. So on the right-hand side, that's what happened. Let me plot the Betti numbers of the complex part of an intersection of quadrics as a so here it goes b0, its value, b1, its value, and so on, up to the dimension here. And here is the middle Betti number. But let me just plot the case for simplicity, k equals 2. So I'm intersecting two quadrics in CPN. Well, this is the Betti numbers of this intersection. How do they look like? They're all ones, except the middle one. And the middle one, it's n minus 2. And here is 1. So if you give me two generic quadrics in CPN, you intersect them, then the sum of the Betti numbers, so the number of the area below this, area is the sum of the Betti numbers, is 2n minus 2. The middle one is the biggest, so it's n minus 2. And then aside from the middle, they're all ones, all one. So it's connected. It's say b1 is 1, so there is just one independent loop, and so on. And then all the complexity happens in the middle. So what I want to tell you now that here, if I take expectation of the real part, what I get is ideally the square root of this picture. Let me tell you the result more precisely. So Let me just tell the result for the moment just for the case of two quadrics, which is the analog case of this picture, because I made this picture only for the case of two quadrics in a complex projective space, intersection of two of them, so two quadrics. Okay, so if I take the expectation of the sum of all Betti numbers, so I'm intersecting two random quadrics in RPN, and I take the expectation of the sum of all possible holes there are, then this is n plus 2 over pi, square root of pi, n to the 1/2, plus big O of n to the c for every c in 0, 1/2. So up to so this term, it can be as small as you want as compared to n to the 1/2, and these constants are exact. And before I tell you more, let me just rewrite this as n plus, actually let me just minus square root of pi over 2 the gap probability at 0 plus big O of n to the c. Moreover, so this is the sum of all of them. That means that the area here, when we take the expectation, it's going to be that number. But moreover, this is the way they distribute, and that's I think the most interesting part. So here now I'm going to plot the expectation of the Betti numbers over the real part. So here's the dimension of our set, so it's going to be n minus 2. Here it's n minus 2 over 2. All right, so there is a neighborhood here where something's going to happen. So here it's 1, here it's 1. So maybe let me just do, this is the midpoint. And there I take a neighborhood of size n to the alpha for every alpha in 0, 1. And here I get something, and the order of the peaking is n to the 1/2. And here is 1. So expectation of bi here, it's 1 plus big O of n to the minus m for every m bigger than 0. So what I'm actually experiencing is that I take the square root of this picture, and this is what happens. So away from the middle Betti numbers, expectation is going to be 1 with very high probability. So probability is the Betti number is going to be 1 with very high probability. And in the middle, so here we got everything is so this size here is just 1. Everything is it's like a delta function. Here we under some rescaling, we approach this with a neighborhood of size n to the alpha for every alpha in 0, 1. So compared to n, this is smaller and smaller and smaller. And the order of peaking here, it's a square root of n. So it's really the square root up to a constant factor of this picture over here. And moreover, let me just say, so you see, ideally you can say, well, take two quadrics, intersect them in RPN at random. It's very likely that this intersection is connected, right? Because B1 is here. So it's very likely that it is connected. In fact, as long as you fix I, the expectation is going to be 1 as long as I doesn't depend on n. Because when you take n large enough, this I is going to stay here, far away from n divided by 2. All right, so maybe I should tell you a little. So why does the random matrix theory enters the game? And it's clear because of my definition already. So because for me, a random quadratic form is a quadratic form whose corresponding matrices is a GOE matrix. So it's clear that at least the problem can be formulated in the random matrix theory setting. But what I want to do actually is I want to tell a little more. So the point here is that to study the topology of intersection of quadrics, we need somehow at least some deterministic formula first. We need some deterministic method, and then we apply the random machinery to this method. Okay? So maybe I'll just spend 2 or 3 minutes telling what is the deterministic counterpart. So here are the ingredients. I'm given k quadratic forms, right? I immediately replace them with the corresponding symmetric matrices, Q1, Qk. And remember, I want to study the common zero locus of this. So my goal is to study topology of where they all vanish. So intersection of all these quadratic forms. Quadratic forms are immediately replaced with this. OK, so what I do now, I consider, so you see now, in the space of all quadratic forms, I'm given some quadratic forms, Q1, Q2, Q3. This is the set of determinant 0 again, and so on. And what I consider is, say, the span of these quadratic forms. So what this actually is, it's a random k-dimensional space in GOE. So if I have 2, I have a random plane in GOE. If I have 3, I have a random 2-dimensional space in GOE, and so on. And there are the ingredients. First ingredient is just mu is the maximum that the function number of positive eigenvalues attains over this space. And the next ingredient is the intersection of this space with the object I defined at the very beginning, so the set of singular matrices. So if I have a random plane in GOE, so the ingredients are the maximum number of positive eigenvalues that a quadratic form in this span has, this mu, and the topology of the intersection of this plane with determinant equals 0, which for us are just a number of singular lines. So the number of lines in this plane, well, the determinant of a linear combination of these quadratic forms vanishes. It's just going to be this. Okay? So this is given by the determinant of x1 q1 plus xk qk is 0, and norm squared equal 1. Once I have these ingredients, this is just the 2 ingredients I need. I collect them into a table here. And this table has k plus 1 columns and n rows. And then the first column, it's filled with all zeros, and there are mu zeros, and they're all ones. The last column is filled with all ones, and there are n minus mu ones, and then all zeros. And the middle here, this part here, it's filled in with numbers, and this comes. The way this number arrange into this comes from algebraic topology. But the only important part for us now is that the sum of all the numbers that I see in here, so let me name this S, so the content of this part of the table is just going to be the topology of this plus n minus 2 mu. So in particular, say, if k equals 2, inside here there are numbers. They're arranged in some weird way, possibly. But the sum of all of them is just going to be n minus 2 mu plus the number of lines where the determinant vanishes in the span of these 2 quadratic forms. OK, these are the ingredients. And then there's a theorem. That says, OK, now how do I read the topology of x out of this table? Well, if I'm interested in the ith by the number, let me just start from top, move down by I. So we arrive here. And then let me make the sum of all the elements on this diagonal. So the sum of all this, it's going to be the ith by the number plus an error. There might be an error. And if I'm interested in the sum of all by the numbers, it's going to be just a sum of all numbers in this table, sum of all numbers in the table, plus an error. In fact, this error is always positive. So this at least gives an upper bound. And in general, as long as the number of codecs is small and the number of variables is large, that's good. So that's exactly what we are working with. So we have few quadrics and many variables. And so what happens is that we can study the limiting behavior of this table. So let's see. First of all, the maximum of the number of positive eigenvalues on our space. So we have, say, I have two symmetric matrices, GOE matrices, and then I consider all possible linear combinations. If I only had one, then say the expectation of the number of positive eigenvalues is close to be half. But if I have two of them and I consider all possible linear combination, what is the expectation of the maximum that I can reach of the number of positive eigenvalues on this on all the span? And then the result, and this is using say actually the state of the art of Wigner's semicircular law combined with some epsilon net argument, is that the expectation of mu, so now I'm taking the statistic of this table. So I'm taking expectation of this table and then asymptotic of what happens. Because then if I have some asymptotic, from this asymptotic, I deduce result on the cohomology of x. Here is x, using this theorem. So the expectation of the number of the maximum of the number of positive eigenvalues is going to be half plus big O of n to the minus m. Oh, sorry. So that really means that the limiting shape of that table, it's actually that this mu gets close to half, n minus mu as well gets close to half. So S gets squeezed somehow, squeezed of a size n to the alpha for every alpha between 0 and 1. So this size here gets smaller and smaller and smaller, and this number of ones gets bigger and bigger and bigger. So the limiting shape of S, it's really something like this. There is all ones here up to the middle, and then all zeros here, and then all ones here up to the middle, and then zeros here. And then here, there is a very tiny compared to an S that gives some contribution. All right, this immediately tells us that, you see, the number of columns is getting bigger and bigger. So the number of columns is fixed, and the number of rows is getting larger and larger and larger and larger. So if I fix a point here and just move along the diagonal, if n is large enough, I'm not going to meet S. I'm just going to have a 1 here. So look at this table and take a point here. Now take the diagonal here going down. And now let the number available go into infinity, right? This diagonal is not going to hit S, and it's not going to hit this other part. It's just going to be this one, and then all 0, 0, 0, 0, 0, 0. And then I can immediately use this theorem and say that the ith Betti number, it is this just the sum of the elements on this diagonal. And this immediately tells that not just for intersection of two quadrics, but for k quadrics. For k quadrics. Away from the middle, expectation of Betti numbers is going to be 1. With, say, plus big O of 1 to the n. I don't know what's happening in the middle for k quadrics in general. Here it's an open question. And then if I have 2 times at the end, hopefully if someone asks a question, I'll tell why this is extremely interesting. So the only thing I want to finish with is saying, at least for the case of 2 quadrics, how do we get this asymptotic with this 2 order of precisions? Again, I'll look at this table. And this table, it's a squeezing, and then it's stretching, right, this way. So all the Betti numbers away from the middle, they're just going to be 1. And those in the middle, they just come from this part of the contribution that I told you, this S. And I told you that for 2 quadrics, S is just going to be essentially the number of singular lines, plus n minus 2 mu. So this in expectation goes to 0, because expectation of mu is n1/2. So I have just to compute on average how many singular lines there are. So I have a random plane in GOE, right? It's random. And then I want to see how many intersection of this plane with determinant equals 0 there are on average. Well, this is the integral geometry formula. Averaging the number of intersection over the orthogonal group, I get exactly the volume of that set, normalized by the volume of the sphere of the corresponding dimension. So I can possibly plug in this value here and get this asymptotic here. How much time do I have left? 5 minutes? Is that okay if I spend 5 more minutes? Okay, so I want to spend 5 more minutes in telling why. So what is not known here now is what's happening in the middle. And I just want to tell why the behavior in the middle, at least for the case k equals 3, it's extremely interesting. So in the case k equals 3, the behavior in the middle, it's going to be the sum of the Betti numbers of the intersection of our plane, this is dimension 3, with determinant equals 0, right? So what is this? Let's just give to the plane coordinates x1, x2, x3. So this set is just going to be determinant of x1, q1 plus x2, q2 plus x3, q3 equals 0, and norm equal 1. So what we have here, it is a curve on the sphere. So this is a curve, say, this is just S, sorry. S is a curve on the sphere, S2. And in fact, we can even forget about this equation and then take the projectivization of the curve. So it's going to be a curve on RP2. It's a smooth curve. And it's random, right? Because the equation for this curve, it's given by these 3 random matrices. So it's a random determinantal curve. All right, so if I could estimate the number of components of this curve on average, then this number of components of this curve on average is exactly the number that fits into here. And it's a number that at the end it's going to give this part here for the corrections, for the area in this middle part. But why is this interesting? The reason is that you give me your favorite curve, real algebraic curve, as long as it's not empty and of degree 2 modulo 4. So as long as the curve you gave me has not degree, say, 4m plus 2, and it's empty, as long as it's not this curve, then I can find you 3 matrices such that this curve can be written in this way. So you give me a real algebraic curve, and then just assume it's not empty. I'm going to find you 3 matrices such that this curve actually arises in this way. This is called a determinantal representation of the curve. And all curves arise in this way, except for this curve. All right, so for example, if you give me this hyperbolic curve, so a maximally nested curve, so a curve of degree d half, of degree d, sorry, with the integer part of d divided by 2 components, one nested into the other. This is called a hyperbolic curve. Then, and this is a theorem of Vinnikov related to Lax conjecture, you can find 3 matrices such that at least one linear combination of them, it's definite, it's positive definite. So there exists C1, C2, C3, such that C1, Q1 plus C2, Q2 plus C3, Q3 is positive definite. So this model, oh, by the way, this curve has degree n, the size of the matrix, right? Degree n. And it's widely studied because of this problem of realizing a boundary of a convex body by intersecting with some slicing the cone of positive definite matrices. And in a sense, this is exactly the solution that Vinnikov gave to the problem when we want to realize something like the simplest convex body that we have as the intersection of the positive definite cone with the hyperplane, but you could say more, right? And also this is related to this problem of flux, of finding the maximal dimension of a subspace in the space of symmetric matrices, which is on which the determinant never vanishes except at the origin. And so this problem could be put in a random form as saying, what is the probability that this curve is empty, for example? Well, I'm going to stop here because I think my time is over. Okay, thank you for your attention.